First of all, thank you for hosting us. We're honored to be here. We hope to give you an insight today about the latest developments in terms of Glulam and in terms of connecting systems, connecting technologies. We are producers of Glulam structures. We do engineer Glulam structures, and we are as well testing and the connecting system on a high load level. Now, that's not just a picture of a nice remote place in Switzerland. That's where we come from. Our factory plant is about in this location here. Sometimes I ask myself, I shouldn't be working there, I should be on holidays. But nevertheless, it's a nice place to work and it's very picturesque. But that's a picture in summer. In winter, it can happen that winter looks like that. Due to global warming, I will talk later on about global warming, it can look like that. So what I want to say is, structures, people, is being put a lot of strain on. It's sometimes the challenges we do face in Lungen and of course as well in Switzerland. Here it's probably a bit different. You have the sea, you have the wind, you have mostly rain. With us here it's in winter, snow. Now, who are we? Neue Holzbau has been founded in 1983. We are quite a young team. These are all the members of the board, all in their 40s, except this guy here. It's my boss. He is becoming 60 this year, but he will hand over next year the responsibility onto this guy. We are 55 people's employees, so means we are a small to middle range company in Switzerland. Now, you have to know, in Switzerland, 90% of all employees are working in small to middle range companies. We do have UBS, we do have Nestle, we do have CS, but most of the employees are working in small and middle range companies. That's our culture, actually. Anyway, if there are questions, please feel free to ask. I wouldn't like to have just a monologue here. If there are questions, or if you do not understand my Swiss style English, please correct me. But feel free to ask questions. Whenever there are questions arising, feel free to ask. Now, we have sort of four pillars, 4 columns where Neue Holzbau stands on. The first one is the research and development department. It's the smallest one, but probably one of the most important one. Then we do have the engineering department, approximately 9 people, all engineers and all with a trade, apprenticeship as carpenters. Then we have the sales department, which are selling the timber structures. And in the end, most important as well, production department. So we are in a close contact with each other because you can't sell something, you can't produce, you can't calculate. It's always a constant information with the projects we are facing, because normally we do not face normal projects. We face rather complex structures, and that's where we're specialized in. Myself, I'm 48, married. I have a son which is 13 years old. Yeah, a teeny at the moment, so. But I've been carpenter as well. I did my college, then became a carpenter, then became an engineer. So all of our employees do have a trade in timber. Reto itself, he is architect, but has been a joiner. We talk about 20, 25, 30 years of experience with timber. And to me, that's more an emotional thing. Working with timber is, to me, emotional. It's not just a technical part, it's not just a calculation I do. I've been doing this all my life. And when I became a carpenter, I have been working, the joinery has been done by hand. I still did it, learned it the traditional way. Not with heavy machinery, not with big machinery, traditional way. And the last 30 years, there has been a huge change in terms of designing, in terms of production, in terms of possibilities, and in terms of projects. And that's what I would like to talk about, that big change that happened. Earlier days, where are we coming from? As said, Neue Holzbau has been founded in 1983. Before Neue Holzbau was founded, it was just Holzbau. And Holzbau AG in Lungen covered the whole process. There was a sawmill, there was a carpentry, there was a joinery, there was a producing of Glulam, there was a cabinet makers, there were as well windows being produced. And in 1983, due to problems within the market, we decided we skip all of it, we concentrate. One company concentrates on the producing of Glulam and structures, and the other one, these were the joiners, they became Top Acoustic. Probably you know Top Acoustic, I don't know. It's the biggest sister company. We are two separate companies, but they deliver all their products throughout the world. So we realized in producing the big structures, the big beams, the Glulams, we can do that too. And we took their experience actually and started to export our products, our structures, our knowledge throughout the world. And I say throughout the world, it's Australia, it's Singapore, it's Kazakhstan, it's Russia, but it's still, let's say, a smaller amount of structure we are delivering to the export. Most of it is happening within Switzerland. But you see here, we are used for a long time to work with larger structures. Though, if you look at the installation process here, health and safety, there are no helmets, there are no boots, no netting, nothing. And that changed a lot. Here, the 1960s, we started to produce Glulam. And we've been the first one actually who had a patent or a standardized system for tennis halls. We've been delivering standardized tennis halls in timber in the 60s, which sort of was the latest state of the art in terms of standardized halls. But that's how the production did look like. Heavy equipment, we are used to large structures. We have been using heavy equipment for a long time. And as well, this picture here shows a wall build-up which has been patented in Lungen. It's as well the culture in Switzerland. We do not need any approval, official approval. If you invent something, you can do your own testing as a company. And if the tests are okay, you can implement it into market. In Germany, it's unlike in Germany. In Germany, you need an approval official. You spend 100,000 francs, 150,000 francs. You wait 4 years, and then you get the approval, and then you can implement your idea into market. Switzerland works a bit different. Of course, for the export, we had to get that approval too. But let's say in Switzerland, it's much easier to be innovative. That's why most of innovations in Switzerland are coming from these small companies, not big ones. These are the small ones, which have an idea which can implement their product within the market. So there is a culture as well of being innovative. Today, how are structures looking today? What we realize is higher expectations, high requirements in terms of forms, in terms of species. Let's say species, we have oak, we have spruce, we have beech, we have combination of these are test samples, of spruce and beech and spruce and ash. That's what we face here today. And this hotel is Sami Sabiris Hotel Jedi in Andermatt, where we delivered actually just a load-bearing structure. Curved structure had to be top quality. And to be honest, I could not afford one night to stay there, but still is a very lovely structure. As well, in terms of size, we built a new fabrication hall in 2010 with the idea to match all the requirements in terms of the size of the structures. And right now, tomorrow, we hand over the latest production hall because the size was too little already. This fabrication hall is 8 years old now, too little. We had to enlarge actually our production just because the projects get bigger and bigger. Here what you see is a bridge. The different colors you see here are the different species. As an engineer, I always play with strength classes, with species. I say, in order to minimize actually the size, I want to sell not a lot of timber. I always say I want to sell just small amount of timber, but with a lot of service being done to it. So here what we have is ash. Up here is the highest Glulam strength class in spruce, and then there's a spruce, and here is ash again, ash again. We do play with it. It's 59 meters in span. has been pre-assembled in 3 segments, being transported to site in 3 segments, being assembled next to the river at full size, including cladding, including roofing. Then we took the biggest crane available in Europe and lifted the whole thing in its place, just in order to avoid scaffolding, because this has been massive. The costs have been massive for scaffolding within the river. Just wasn't possible. So that's what we face in terms of size, in terms of structures, and that's what we play with. When I talk about Glulam, there are 2 sites. We started off 20 years ago in doing research and development on Glulam. First, just on spruce. This is a normal spruce, sort of little part, which has been tested, the finger jointing here. And then we realized normal Glulam is GL24. With spruce, we can go up to GL36, means 1.5 times the strength. And then we realized, why not going higher in testing beech or ash? People often think we can take oak as well. But in terms of bending, oak is not better than spruce. But we realized this is the way to go, ash or beech. And then in the end, we realized there's no sense in having super duper Glulam, high strength Glulam, without having a connecting system, what you see there. We started to invent or test a new connecting system, which you can see there is just gluing in rods into the timber. And one glued in rod, diameter 16 mil, takes 90 kilonewtons, which means 9 tons. You do not have any more these huge plates, these huge bolts, and you don't weaken the timber in cutting it up. You just glue that in. That's the concept we are working with. So, in terms of timber, it's not a short-term thinking, it's a long-term thinking. What you see here is a forest in beech. What happens in Europe due to global warming? Less and less spruce, more and more beech. That's what we experience in Switzerland, that's in south of Germany. If you ask the workers in the forest, 25, 30 years ago, they had much more spruce there, and now the beech is taking over. And what do people do with the beech? They burn it. That's the best timber to burn, actually, to grill. It's the wrong path to follow. So we said, we do need actually to use that beech because it's perfect timber. Of course, it's difficult to work with. It's not easy. Puts a lot of strain on the machinery. It's put a lot of strains on the men working with it. It's not as easy anymore to drill in a screwer because it's a hardwood. But that's what we want to do. We want to use this timber in terms of knowing, in terms of long-term thinking. We know in 30 years, beech will be much more than spruce if global warming doesn't change. That's what you don't know. But that's what we're facing, actually. In terms of machinery, it's the same thing. If you use hardwood, high-strength Glulam, and that's the normal thing, you do finger joint the laminates here. You glue it and finger joint it. All of a sudden, it's not the timber that governs the strength class. All of a sudden, with hardwood, it's the finger jointing of the laminates. You cut the laminate, you take the knots out, those pieces that are weak, you cut it out. You finger joint it, you add the laminate to 30, 40 meters. But then you have to make sure that it's not the finger jointing of the laminate that governs the size or the strength class. It must be still the timber. So we had to do a lot of research on that finger jointing. We use different glue, different time to press, different pressure. We even have to put a bit of humidity on it, steam on it, in order to make sure that the finger jointing is perfect. Working with Glulam in hardwood, as the same with Hotel Kolm, puts a lot of strain on the machinery. And people working with it, and as well the connecting system itself. But anyway, the difference to the earlier days, 25, 30 years ago, one said 2 hours in the office equates to 2 days work in the production. Today, it's the opposite. 2 days of working in the office, planning, equates 2 hours for the machines. So those machines, this machine here is 35 meters long, 6 meters wide. It's meant for large structures, and it's such a speed. 2 hours and it's done. Of course, later on, you still have to do some joinery by hand, but basically, most of the work is now done with the machine. So the planning department is always getting bigger and bigger, while the production stays the same. That's what we face today. Now, what are we doing at neue Holzbau? First of all, we have the planning department, which means 9 engineers constantly calculating structures. And the point is, when designing timber itself, the process is exactly the same as with concrete, as with steel, as with any material. The difference is always the connecting system. Here in England or UK, I do see a lot of perfect engineers in terms of steel, but they use details for steel and apply it onto timber. And then you see big plates, big dowels, big bolts. You see 30 bolts here, 20 bolts there. For us, it's not the way to go. We have the Glulam, where we do a lot of research on. Means we are able to produce GL40H, which is double the strength as the normal Glulam. We have different species, from oak to Accoya to ash to beech, and it always needs a lot of research. So not any producer can do it. You need to have a research department as well. It's a joinery itself. Big structures require actually big machines as well, and quite a bit of experience in terms of doing the joinery. GSA technology that I've been talking about, it's the glued-in rod. And important, if I say a 20 diameter bolt takes, for example, glued in, takes 14 tons, you need to make sure that that threaded rod takes 14 tons. It's not when you have 30 bolts and one bolt is missing, you can say, okay, there are other 29 bolts, it's still okay. So it means quality control is immense. If you work with large structures spanning 59 meters or more, you really need to make sure that the quality control throughout the whole process is being done properly. Means in terms of producing Glulam, you need to make sure that it's GL40 and not GL36. In terms of connecting systems, you need to make sure that all the threaded rods do withstand, have the capacity to take the load, and as well, in terms of time-wise, being delivered the structure to site, you can't leave the crane for 2 days just on site, because that crane costs you probably 2,000 pounds, the big one. Or the biggest one was about 20,000 pounds per day. That's what you face. Or then as well, research and development. If you have a problem, or if we have a problem, we can actually customize the connectors. We can test it, we get results, and within a week we do have these results, and then we can implement it. So that's how we work. Logistics itself, I mean, in Switzerland, it's possible up to 40 meters. That's the maximum span probably can transport. If you go into export, you have to use a GSA technology because you splint the beams. If it goes to Australia, you can't transport 30-meter long beams to Australia. You need to put it into a container, and so you splint it, you assemble it on site, and you deliver it to site. Assemble it back. And we do not have 30 bolts here, 30 bolts there. We have a threaded rod, which is fixed onto a steel part, what you see here, for example. This is quite simple. This is a small scale mock-up. But then we work threaded rods, which are fixed onto a steel part, and on the other side exactly the same, and you use 2 bolts. You don't have 30 bolts here with washers, 30 bolts there. Normally we try to have 2 bolts to work with, and that's it. So speed on site is crucial for us as well. Then we have Baubuche. We are not afraid of working with other materials. Baubuche is a German product, perfect product as well. It's GL70, the best timber in terms of strength classes you can get on the market. So we do work with this as well. Or timber concrete composite decks. I mean, I'm not fond of using everywhere timber, just where it makes sense. So what we're producing are decks where you take the timber beam, you add the connector, and then you pour concrete on top of it. And so slab is concrete, and the beam is timber. We work with different materials. In the end, Accoya. Probably you know already Accoya. This is this one here. This is just acid-treated timber. I think 20 years guarantee.
More than
50 years guarantee. If you put it into the soil, you have 20 years directly, and I think you leave it exposed, you have up to 50 years guarantee. The only thing is, using Accoya, the connectors need to be stainless steel because it's acid-treated. So you always have to know a bit what you're dealing with. The connecting system, any connecting system with Accoya needs to be stainless steel, so it's a bit more expensive than just taking normal steel.
So you're in this slide. Can you explain a little bit more about timber concrete composite? Because usually you have timber structure because of the beauty and the structure, so you need to cover it. Sorry, can you give us examples?
Yeah, timber concrete composite decks we use often for office buildings or for high, when you have high loads, live loads, for example. If you span 12 meters, then we use timber concrete composite decks because the deck itself is 12 centimeters concrete, that's it. And then you have the beams spanning 12, 14 meters. So you can span 12 meters in timber purely, but then it gets more expensive. Concrete itself is quite a cheap material. We calculate with probably 50 pounds per square meter for the concrete itself, poured in, installed. And so this is, you save a lot of material then actually. A lot of material is saved. That's why I use it. It's quite an economical solution for long spans and for high load level. Now, GSA technology. Its components, I don't have a thread at the bottom here, it's quite simple. You have steel, which we know. We do take the steel rods in. We do test the steel rods because we want to know, is it 300 newtons per square millimeter, or is it 320, or is it 325, the load, the capacity. We take a few kilometers of the same steel rod and we test it. Then you have the timber. Timber, we know, we have been working with it for years. And in the end, it's the resin. Resin, we had to do a lot of testing on it as well because people do not know, but resin has a creeping as well. And we do not want to have creeping within the resin. So we are using a special resin which doesn't creep. And you glue it in, and in the end, one 20 diameter rod takes 140 kilonewton, which is 14 tons. Or 16 diameter mill takes 91 kilonewtons, which is approximately 9 tons, with one connector. And then, of course, the connector is glued in, which means basically not visual. And secondly, for fire requirements, protected from the timber. But you need to make sure that the resin doesn't get hot. If resin gets hot, loses its capacity. So for, let's say, 30 minutes, we use 40 mil covering of timber. For 60 minutes, I think we use 50 to 60 mil. 90 minutes fire requirements equates to, what is 90 mils, I think. 90 mils in the end. But you need just use a bit more timber and it's done. That's the advantage of the GSA technology. For 3D structures, you see as well, we can customize, actually, these details. Of course, engineers try to always implement the standardized connectors, but for special projects, you need to customize all these connectors. Now, probably you know already the fact, but when I started to be an engineer, the standards have been this thick. I've been 25 years in the market, and there's a third generation of standards I experience now. The second one was this thick, third one was this thick. Formula to calculate connectors. First one was this long, first generation, second one, and the third one is this long. Calculations do get more complex due to the fact that we have higher requirements and higher expectations from you guys as well. It's not a bad development, it's a good development, but everything gets more complex. So people do calculate more, and what we did is actually we said we need to standardize all these connectors in order to make sure that we don't spend a lot of time just calculating. As an engineer, if you're happy to, normally you're fond of calculating. You can spend hours on calculating, but that's not the idea in the end. The building is not here for me that I can calculate. It's the opposite way. I should serve the building. That's my aspect. That's my idea. So we did standardize all these different connectors. For example, if you have just a normal column to beam connector, I mean, with four rods, you get 36 tons being transferred into the column. 4 rods hidden. That's the capacity. Or here as well, if you have, there's a nice detail here for a column. Same here if it's fixed, rigid onto concrete slab. That's how it can look like. Or if you have a connection in the ridge, you have 1 bolt. You do not have 7, 8, 20 bolts and plates and cut up timber and so on and so forth. Or if you have a continuous column and then a beam onto it, it's GSA R. R stands for ring, for example. It's the same connector as here, for example. Then you can use this. Of course, if you want to have fire protection, then you need to have a plug, timber plug or a ferrocell plug in the end to cover it. But this is a possibility. Or if the bracing system, that's what carpenters are struggling most with, even engineers, to have a nice bracing system within the roof. That's how we work with. Standardize connections.
Sorry.
Or, yep.
Do you never work with connections that have no steel pieces, like the one on the top left? What's the need for that bolt?
This one here.
Yeah.
You have half the size of the ring on the one side, the other half on the other side, and at the end you put 2 small rings on top of it, and then you bolt it. The idea as an engineer is if I design structures, I want always the steel to fail. I do not want the timber to fail, because if timber fails, no, I don't have it with me, here, you get this one here, sun rupture. You do not want the timber to fail, because kaboom, and it's broken. If we have steel failing, that's the advantage of steel, it flows. So we always design the connectors to be the thing that governs actually its capacity, and within the connection, it's the steel that's failing. Because then the structure doesn't break, but it has a deformation in it, and you realize. That's the important part. Often engineers are not designing anymore according to these standards. But I always want the steel to fail. So if we glue in rods, what we often do is as well, we minimize the rod which connects here. We minimize its size, its diameter within here, just for 2 or 3 millimeters, in order to make sure it's the steel that then fails. And in the end, you just have a deformation within the steel, and you realize, hey, too much load on it. It doesn't break, but you have a deformation. And that's how we want to design these structures. So, in these terms, steel is a perfect connecting system. Timber wouldn't work like that. Timber just has a rupture and it's breaking. And here is the timber concrete composite deck here. Spanning, I think here was, in the end it was 12 meters, 13 meters. You see the glued-in rods, the concrete that is poured on top of it, and then you have connection between timber through the rods within the concrete, interacting with each other. And there you need to be careful as engineer and as architects. I've been involved with the Northwest Cambridge development as well, and it has been very difficult because you have so many different materials. You have brickwork acting with concrete, reacting with timber, reacting with steel. All different materials with different behavior interacting with each other. What I normally do, if I say for the lateral stability of a building, I just take one material, that's it. Either it's steel, or it's timber, or it's brick, or it's concrete. But there, the engineer has been mixing everything with each other, and this is very, very difficult to calculate. The art of the engineer today is to simplify that whole process in terms of connections and in terms of materials as well. It's, of course you can calculate. You can calculate this, but it takes days. And I don't want to calculate just days, day long, just in order to make sure that everything is interacting with each other. If I take timber, alone timber, I know how it behaves and how it reacts, and it's easier than the other way around. So when designing or building in brick and steel and concrete and timber, make sure that the interfaces are solved correctly. That's often the art and the problem or the challenge in the whole thing. The interaction between those different materials. If we deliver structures, for example, to Australia, we just finished off a school in Australia, you have this detail here. You can't deliver 30-meter long beams like there. We had to split it. It's one container is 12.5 meters, I think, around there. So you split the beam, and then in the end you assemble it on site. And you see here 2 bolts, there 2 bolts, finished.
So what's actually inside there? Is it a series of interlocking rings?
It's actually this one here. It's this connection here. If you can have a look, it's like normally it's the GSA anchor is fixed onto a steel part. On the other side, exactly the same. And then you have the bolt here, bolt there.
Pin them together.
Pinned. It's an easy pin and socket system. And if it has to match fire requirements, actually, of course here you see the steel element. But then what I did in Australia is just enlarge in terms of size the beam, and then it has been covered with timber, in order to make sure that it matches actually the requirement of 90 minutes. I think it was 90 minutes. So. The same, if you have a portal frame, you can do the same in the corner connection here. It's a bending stiff connection. Normally you see either huge plates or a ring with bolts, and that's not the state of the art anymore. Because here you really do add 3 bolts there, 3 bolts there with the thumb, and not with a hammer, and you're done with it. So time on site is much less than with other systems. I saw, I think, what was a year ago or so, more even. This is an old sample, I think, yeah. This is now Baubuch, a German product, produced for a frame. And this is the fabrication hall for the new Pilatus aircrafts, PC-24. 90 meters long, 95 meters long, 50 meters wide, without any support in the middle, using GSA technology and Baubuche. And time limit was so crucial, I had to go and help within the production. So I helped producing actually these frames. And I was responsible for putting varnish on top of it. Varnish in order to protect Baubuche when it rains. And that's the part here in England. It rains more than in Switzerland. And that's the other thing. You do not have a lot of time on site. You need to make sure that the speed on site you're finished quickly. You want to protect the structure. You want to make sure that the roof is on top of it.
Sorry, can you explain the connection there?
This is prefabbed actually here now. What we try to do as well, prefab, pre-install as much as possible. So these frames, they were delivered in one piece on site. So what we did is gluing rods in here and gluing rods in there. But you don't need any steel part in between because it's delivered as one piece. It's the same as here. That's the one here. Just glued in rods. And here you see, there you fill in the resin, and here the resin is coming out to make sure, and then you put the plug in. Our latest child sort of is this connection here. It's a continuous beam running through the whole office building, and then a continuous beam being interlocked with the other sides on each other. It's used for a grid line of 7.5 to 7.5 meters approximately. So you have continuous column here and the beam being fixed onto that column. And this beam is acting as continuous beam, sort of like a frame. We do not need any crosses anymore to stabilize the building. It's because we have a frame within the structure itself, we can use it as a frame for the lateral stability of the whole building. Although we are fixed at the moment on 7.5 to 7.5 meters. If we go higher, the size gets just very big and more expensive. So in terms of economical thinking, at the moment 7.5 times 7.5, that's the grid line we're working with at the moment. And if you talk about office buildings, you see this, ventilation. Where to go with the ventilation? According to normal standards, you can penetrate the beam maximum a third of its height. That's the maximum you can do. In the reinforcing these penetrations, including rods, we can go up to half of the size of the beam without having to minimize its capacity. So reinforcing these penetrations, you do not have to do any calculations. You can design it as normal and then reinforce the penetration and be done with it. Of course, but it has its price. This one costs approximately £300, such a penetration. But that's the way to go. We do realize, and often these ventilation planners are way behind. They come in the very end of the. Before it has been the electricians. We said, oh, the electricians, they always drill and make holes. And nowadays, it's not the electricians anymore, the ventilation planners. They're way behind. If planning a timber structure, we're always ahead because you pre-install, you need to make sure everything works and it's fine and pre-planned. And then at the very end, they come and say, we need a penetration here, there, But then we still have the possibility in using that technology because we do not have to minimize its capacity. But yet still the idea is that even those planners are ahead and not behind in planning these buildings. The resin itself, if you use resin to interlock these connections or to assemble these connections, that's the most expensive part. So we said we try with the grouting as well. The bridge you saw, that's the segment when putting the segments together of that bridge, the 59-meter long bridge, we have been using the first time grouting. We tested before and it has been working. So grouting can be a different material which we are using as well if assembling these structures on site, because if you use resin on site, you need to make sure Celsius degrees 20 at least, humidity, no rain, no dirt, and so on and so forth. So gluing in on site, we do want to avoid. That's not the way to go. Especially in England with the rain. It's always raining. So grouting is easier to handle. Of course, visually, not the best way, but since it has been a bridge and this part has been covered, it's not a problem.
So it seems like your systems relies a lot on the resin or the grouts. So in other words, the structure is only as good as the resin is good.
Yeah,
So
exactly.
you make your own resin?
Yes, we developed that resin. We're the only ones, because as I said, no shrinkage within the resin and no creeping. Mostly no, and this is a non-creeping, non-shrinkage grouting as well. That's what you need to make sure. But this resin has been developed specially for us. It has been a lot of research and a lot of money done, a lot of money being used to do the research on timber and on the resin itself. This is a pretensioning system, which is used not so much only in special structures. If the architect really wants to keep the sizes small, super small and thin for large structures, then we use this system here. But here is as well exactly the same. Behavior of steel is a bit different than the one from timber. And timber does have a bit of shrinkage, and you need to make sure that the calculations are being done correct. So you need to make sure if this is GL 48, it must be GL 38 in order to make sure the behavior is working. So pretensioning is working, but a bit more calculations have to be done. And of course then research development. Here you see the frame. As I said, if we do have face a problem or a challenge, let's put it as a way as a challenge, within a project, we do the research and development and get results within, say, weeks. That's the advantage what we have. Professor Gary has been working for the Federal Institute of Zurich for years, and then of course he got retired, and I say he is like a child. If you don't give him work, he is testing his own thing. We decided that we will build a research center for him, just quite a big room. And we had some ideas, he had ideas, and since then he has been working for us, since he has been retired. So people in retirement, they have a lot of knowledge. And I don't know, he has been spending a lot of time in our factory. And it was the best for us, but if not, this knowledge would have been wasted. So advantages, standardized system, higher level of completion. We do try to pre-install as much as possible. We try to prefab as much as possible. Whenever possible, we deliver the structures finished on site at a large scale. Architecturally pleasing in terms of hidden structures, hidden connectors. Fire regulations, as I said before, you just need to cover, have a cover of timber. That's the advantage actually of the connecting system itself. If you talk about projects, that's the end now of my presentation. UK is fond of where is it? Of oak. It's the most expensive glulam you can get, but they're fond of oak. Of course, I'd say probably historically, you had a lot of oak forests. But yeah, this has been the Jesus College, and you see the columns very thin, very tender, very light. I managed to glue in one rod, but in the end it has been working, but it has been so thin. It was difficult actually, but in the end it has been working. Or this project you probably know. We did produce the mock-up in the room over there and the structure itself. Bloemer-Lehrman was the client sort of. We delivered it to Bloemer-Lehrman. He has been installing it. Yeah. Here you see the connecting system here. all these different segments and glued in rods. Yeah. Has been challenging, but it has been working.
You holding back on something?
Do I? Okay. A lot of sweat was in there, yeah, and sleepless nights as well. But in the end, it's always the idea to make it work. That's our challenge. That's what we want. That's our aim.
Sorry. Well, I remember when we were drawing the base, the connection to the concrete, and going through the idea of the rods that you were talking about. There was a lot of discussions about the separation between the rods and how far apart they had to be in that base so that the moment was transferred.
Yep.
Was that something that, was it your engineers who were calculating that, or was it more Blumer-Lehmann?
No, Blumer-Lehmann doesn't calculate. We are calculating the.
You were calculating.
Yeah. Not me. No, but yeah.
SJB, or do you remember SJB engineers?
No. No, the GSA, it was Thomas Strahm. What is the shortcut was?
No, it's just I remember looking at the drawings that came from your side, and
Yeah.
it was SJB fits something or other. I can't remember
Yeah.
that was the end. But I remember the issue was that some of the engineers from the local architect
Yeah.
were not sure of these rods at the beginning, and convincing. Is there anything in the resin that it's a resin that's supposed to last forever? Is there a durability issue? I never got into that really. 'Cause I was on the road.
The resin lasts forever itself, but if you take a 16 diameter rod and you glue it in parallel to grain, you must have at least 6 centimeters of edge distance to the next one. If it's a 20 mil rod, you need 8 centimeters. Because if you pull out the rod here, it's not, in the end, if you don't minimize the section of the steel, in the end it's just the rod along with the timber that's being pulled out. So you do need a certain edge distance in order to make sure that the capacity of the steel rod is sufficient. And of course, such structures itself. The issue was again the snow. Snow was governed actually the load in these terms and in the end the momentum. So it has been a huge momentum and huge forces being fixed onto that base. Yeah. It's always the snow actually up in the mountains. Yeah, and this one here is Aqua Basileia, probably biggest ring beam ever built. Maybe next picture. These are the columns. If you look at the size of the columns, as well splinted and assembled on site, and if you go back to the ring, same columns. Huge ring. Delivered in 3 segments and then assembled on site. And assembly on site, that's assembly on site. Large structures, and as well if you look at the columns, 3 segments, and up here bigger diameter than down here, because the architect wanted to have, if you stand here as a spectator or any people, he wanted to have visually just the same size of the column.
Sorry, what was the size again?
The size of the column, I don't know anymore. I've been working in the engineering office who designed actually Aqua Basileia. Back then I haven't been working for neue Holzbau, but 4 years later I've been working for neue Holzbau. But we've been responsible for the design of the structure here. So, but I don't remember the size anymore. But
how did the splice between the ring beam segments work? Was it
it's like, oh, do I have a...
Was it glued on site?
No, it was glued on site, and difficult part was actually you need 20 Celsius degrees, you need no rain. We packed it in foil and put in a heating system in order to make sure that the resin has its perfect consistency to be worked with. Yeah, and in the end, it's a swimming pool. You need to make sure that everything is packed in chemical components. So But we used sort of like a rod who has been bent, and the counterpart as well. And then he put in the bolts, and it wasn't just one bolt. There were used many bolts. I think the ring itself, more than 5 meters, and its price, I think was 200,000 Swiss francs, around there. I don't know anymore. It's too long ago. But what I say, everything is possible. Everything. The question is the money. That's always the question. Almost, let's put it this way, almost everything is possible. But special solutions, special wishes, they're just costly. They are costly. Not too cheap. So sometimes it's the architect's task as well to find that economical solution and not leaving its idea unless the customer has enough money. Then it's no problem. But as an engineer, I always try to find an economical solution which suits the architect and the customer. That's the art of the architect. Transportation, as I said before, we try to actually pre-install as much as possible because gluing in rods is cheaper than assembling it on site because we can avoid that steel parts. So we just get this one here. That's it in the end. No connecting system being seen if you pre-assemble it within the factory. Means then transportation is looks like this. This is transport leaving in Lungen. That's our power plant. That's winter now. Normally has to drive over a pass as well. We thought about leaving Lungen in terms of we are at the end of the valley. But then we realized people who work here with Lungen tend to work for 10, 20, 30, 40 years. We do have very little change within the company. If we would go down to Lucerne, it probably would be better due to transportation, easier, but it's more difficult to find people. The change, you change in Lucerne, let's say, probably we wouldn't have people working here for 30, 40, 50 years. So once you work in Lungen, you tend to stay in Lungen. I think in average, it is. In average, I think it's 20, 15, 20 years, in average, or more. So, yeah, maybe it's due to that nice place, I don't know. Maybe it's due to the team, maybe it's due, I don't know. I've been talking about large projects. We're familiar with small projects as well. I say it doesn't have to be large. I prefer smaller projects. Large projects normally do take a lot of effort, a lot of time, a lot of effort, a lot of input. Smaller projects are just as interesting to me as large ones. This is a clubhouse of a golf club, and you see here again 3D structures, round columns, square rafters. To me, just as interesting as big ones. So it doesn't matter what size the project is. Really doesn't matter. Beach for exhibitions. We deliver structures as well for exhibitions now with beach, and yeah, architectural, to me, very nice structure.
Sorry, is it much more expensive to do round columns than square columns? Is the process of rounding pieces something that adds a lot of cost?
Yeah, you produce a square beam in the beginning, and then you join it first on the machine, and in the end by hand.
So there's a considerable added cost?
It is. It's always an extra cost to do it, of course, because the machine is quite cheap. It's the labor by hand that is costly. But still, to us, to me, it's the most interesting work if you can do it a lot of by hand as well, because not everybody can do it. But round columns, in terms of an engineer, is actually the most economical form as an engineer, but in terms of production, not. Look at the tree. The tree isn't square, a trunk. It's round. If it would be economical, in terms of an engineer, if it would be engineering the best solution, tree trunk would be square. It's not square, it's round. So that would be as an engineer, it's the simplest form. But producing this is quite costly. That's the bridge. Light structure, transparent structure. I like that bridge. I designed it. I was responsible for it. A lot of sweat. When they installed the crane and installed the bridge, I was praying everything has, because 59 meters, and you put it in its place, and the support isn't working or at the wrong place, you do have a problem. You really do have a problem. And then it did fit well. But yeah, still a lot of sweat doing this. Or for example, industrial building. This is a carpentry down here with a crane here and the frame on top of it. And in here is the office building, office space, spanning 28 meters, I think, 22 plus here is 5 meters. And on top of here, there are 6 flats. So using the space, here are the flats, here's the office space, and down here's the carpentry. Pre-installed within the factory, delivered in one piece to site, such a frame, and installed in one piece. That's the detail here. Again, ash, here spruce. We do play with material, we do play with species, we do play with strength classes. That's the possibility we have. Not everybody has this possibility, but in the end, here you see, this is ash, the green one, here is spruce, and this is highest quality of spruce, the green one again.
Also the sections.
The sections were, I think, 32 times 600. This one here, I think this is 24 times, this is 600 here. Height of 600.
Is the species, is that cost driven then, to play with the species?
I use it only where necessary to keep the sections low. If I produce the same frame all in ash, I can save on the sections throughout, but yet the cost is still higher. The saving on material isn't matching the price of the material itself. But it makes sense if you just use ash or beech, wherever. You don't want to have large, super large end pieces here because it's used as an office space. So it does make sense. I say just use those wherever needed. Yeah. If not needed, don't use it. Of course, you save on half of the size, but still, the timber itself is still more expensive than using spruce. Portsmouth. This has been the community center, Portsmouth. I think first it was designed in steel, and then we came with a timber solution. As well segmented here, there, a lot of segments there. Delivered to site, assembled on site, installed on site as a ring beam in the end. Here is Milan, Italy as well. Normally Italians tend to use special species of timber. They don't want spruce, normally they... Irocco, yeah, okay. They're designers, the Italians more. You do feel as a Swiss, everything must be special. Or for example, this is a tennis hall up in Burgenstock. I don't know, Burgenstock Resort, the Qataris invested how many millions?
600 million.
600 millions up there.
7 years long.
in the 50s, Bergenstock has been the it place for Hollywood, 40s, 50s. And then actually got forgotten all about it. Now the Qataris are investing there, and they produced, or they wanted to have 2 tennis halls shaped in terms of like a diamond. The idea is that Roger Federer will be playing there as well.
So who's that guy now, the picture?
Sorry?
It's just photo bomb every single picture.
Yeah.
Who is it? Is it a carpenter?
This one here. This is our king, actually.
Yeah,
This is our king. You have a queen, we have the king. He is actually, he is doing the marketing for us. It's the Swiss sport. It's the traditional Swiss sports, which is called wrestling in the sawdust. Those guys are 120 to 140 kilos. You wouldn't like to fight them. So, and he is doing the marketing for us. Up in where our power plant is, we have each year a wrestling event of all the Switzerland, and all the wrestlers are coming, and he is actually he is the one in the traditional Swiss clothing. But he represents Swiss values for us. But actually, at the moment, he's the king. It means every 3 years there is the competition, and he's the latest king, actually. So he would be the king. Okay. This is not a Qatari. Not the investor. Eh? Okay, then Pilatus aircrafts. Delivered last year, 95 meters long, 50 meters wide. And this plane, they have so many, how do you say? Ja, Bestellungen, reservations for planes. They ordered for this summer the second one, even larger. So at the moment we are producing the second fabrication hall for PC-24. I think 145 meters times, I don't know anymore, but huge. And at the moment, production is just restricted for that project, because I don't know how many cubic meters timber there is, but a lot of cubic. And as well, you see here combination of steel, suspension and steel. And it looks quite tiny, but one steel suspension here is this size. One of it. And the beam is wide, is 1.2 meters wide. Yeah.
One element was 16 tons.
I think, yeah, in the end 16 tons, yeah. It looks slim and tender, but at the floor, installing it, it's quite massive. But that's your task, to make it. You're the architect. Thank you for your time. Your vision is our challenge. As I said, almost everything is possible, and we try to make it work in terms of fire requirements, in terms of visuality, in terms of sizes. We try to match your vision and costs. Okay.